Hi, in this video I'm going to go through an example involving a calculation with vectors. In this case, taken from electrostatics, type of problem you might encounter several times over in this course, or maybe already have encountered. But really it's mostly just about how do I deal with vectors, how do I add forces, stuff that for the most part you should already know. But hopefully this will be useful. Let's look at this example here. I imagine I've got three charges, charge A, charge B, and then this other charge, I'm just going to call it Q. This one has a charge, little QA. I'm not going to use specific values, right? You can imagine maybe it's 3 nanocoulombs, something like that, right? And this one is it's negative. I'm going to give you that. We're going to be specific in that regard just to keep things concrete. But, it could be minus 2 nanocoulombs or minus 6 microcoulombs. Who cares, right? Going to leave it general. Just going to assume this one's positive, this one's negative. And then there's another charge here that's also negative. Right, that's going to be our example. And the distances between this one and this one, it's called S. The distance between this one and this one, that is called H. And we're asked to find a force on the charge Q up here. Right. So let's look at this situation and ask ourselves, what is going on? Right? What's going to happen? What's the physics of this? So you've got three charges, and any two charges are going to interact. Right? Now you know from your electrostatics that like charges with the same sign, they repel each other. So if I just take those two charges here, right, they're going to repel each other. So there's a force on this one that's in that direction, and there's a force on this one here that's in that direction. Right, that's the interaction between those two. There's an interaction between this one here and this one here. Now, this one is a positive charge, this one is a negative charge, so they're going to attract. So there's a force on this one that sort of points in this direction. I don't know how big it is compared to that one, because I don't know the values of the charges, don't know the distances, it doesn't matter. Right, but it's in this direction, and there's an equal opposite force in that direction. And there's also an interaction between those two charges here, right? In this case, one's positive, one's negative, so they're going to attract each other. So there's a force this way, and there's a force this way. Right? So now we've got all the forces on each of the three charges. Our physical insight has been, okay, charges interact with each other electrostatically. They attract or they repel. And to find the total force on any one charge, well, I just add the individual forces. Now, in our case, we only care about the force on this one here. Now, you might say, but surely, look at this one here, this is going to start moving, and it's going to change the arrangement. That is true. But we are asked to find the force right now. So, I'm not worried about what happens to this charge next if I wait. I'm not worried about this one either. Maybe they're fixed in place. Maybe if I wait a fraction of a second it would look different, but I don't care. I'm asked to find a force on this one right now. And right now this charge is here, this charge is here. So the fact that those two are interacting, the blue interaction, I don't care about it. I don't care about the fact that this one's also getting pulled in that direction here. And I don't care that this one here gets pushed downwards by that one. I only care right now about the forces acting on this one. And those are due to the red and due to the green interaction. So now I'm going to calculate the strength of each force. So let me label those. Because this one here is due to charge B, I'm going to call this F subscript B. And because this one here is due to charge A, I'm going to call it F subscript A. I want to find the net force. And I already know that just by adding them as vectors, it's going to be sort of like this, to the top left probably. I mean, I guess if the red one was a lot stronger than the green one, it could be just more like to the left, and not very much to the top. But it's going to be somewhere in a direction that's something like this. So my next step is to calculate the magnitude of each of those two forces. So I'm going to use Coulombs Law, or Coulombs Law. So let's figure out the green one. Right, that's the interaction between this one and this one. The strength of it is going to be K times the two charges that are interacting, times Q times QB, divided by the distance between them squared. What's the distance between them? Well, it's just given as h squared. Now, really, because one's negative, or they're both negative, but in general it could be negative and positive, this is going to have some sign. I don't care about the sign. Right? I know which way the force points. So I'm just going to write it like this. Right? The absolute value. The sign really says, is it attractive or repulsive? But I already know that. Right? I've already shown the direction this force points. I know it from the physics. If I have minus signs, I'm just going to get confused. Right? I know the physics says the force is going to be this way with a magnitude given by this. Now there's the other force, right? Fa. I know which way it is. Is it positive or negative compared to this? Well, it's not in the same direction, right? It's at an angle. I'm going to have to take components. But right now, I just care about the magnitude. So what is the magnitude? It's going to be K, right? Coulombs Law, times Q, because this is one of the charges involved in this interaction, times QA, divided by the distance between them squared. What's the distance between them squared? Well, if I complete this triangle like this, I can use Pythagoras to find this side here. It's going to be the square root of h squared plus s squared. Let me call this length L, and I can say that L is the square root of h squared plus s squared, right? It's just basic geometry. You know that. Now, if I square this, because I want the square of it in the bottom, that just makes the square root go away. So I'm going to put h squared plus s squared at the bottom. Right. Now, if I wanted to find that third force, the blue one, well, I'd plug in QA and QB, right, at the top. So I'm going to get rid of that big old, capital Q. But I don't care about the interaction between those two right now. The interaction between those two does nothing to this one. So nowhere in your calculation should there be a term that involves both QA and QB multiplied together. Okay, so Now I know the strength of each one. Now I want to find the total force, so I have to add them, right? We want to add these. But because they're in different directions, I have to add them as vectors. And you know about the vectors, right? It's a basic math skill you need to have. So to add them as vectors, we have to find the components, which means you should really first pick a coordinate system. I think it makes the most sense here, given the geometry of this, to just use the usual one, where this is my x direction, and this is my y direction. Right. It's just simplest this way. Had my chart just been arranged more like this, at some funny angle, maybe some other coordinate system would have been more useful. Okay, so let's add those. So I hope you've got these in your notes, so you can look at it. I'm going to move the paper up a little bit. Okay, so now we're adding the vectors. How do we add vectors? We add them component by component. Right? The x component of one vector plus the x component of the second vector. That makes the x component of the resulting vector, of the total force. So let's add those individually. Let's go in the x direction first. Right? And remember, our coordinate system is going to be x is this way, y is this way, because it closely matches the directions that are relevant in the setup here. Now, looking at the x direction first. FB is straight up, straight in the y direction. It does not do anything to the force in the x direction. So I really only have to worry about this one here. I want to find the x component. So let's draw this again out. Let's draw it. I've got this vector here. This is FA. And I'm trying to add to it this vector here, FB. Right? I'm just adding vectors now. I've done the physics. Now it's just math. Well, this one only has a y component. That's the easy one. Right? This one is both left-right, but also up-down. So I'm going to draw the components. Now, I don't really know the angles yet. Let me call this angle here, let me call it alpha. Could have called it theta, but I want to call it alpha. So the x component of this one, let me write it like this, F net in the x direction is going to be equal to FA. Now this is the x direction here, this is the adjacent, times cosine of alpha. But I have to be careful, right, because this one's to the left and my coordinate system has x point to the right, so this is going to be negative. Right, the length of this just shows me the strength of the force in the horizontal direction, the horizontal component of this, right? And I can see it's to the left. So I know it's a negative it's going to be a negative component in the x direction. I don't hope that somehow the minus signs I have up here or something makes it work out. No, I keep the physics in mind. I know what's going on. It's to the left. And I work with an angle that's smaller than 90 degrees, so I know this is going to be positive. Of course, then I add to this, I add to it 0 in this case. I can see that. But if you want to be more pedantic about it, I could say it's FB times the cosine of 90, right? But the cosine of 90 is just 0. So we see that right away. We don't even have to write this down. This is just for completeness. Okay, I know what this is. We figured that one out. What about this one here? What's the angle? Well, let's look at the geometry of this. I know the sides of this triangle, right? Now, alpha is this angle up here. But that angle up here is the same as this angle down here. See if I can squeeze this in. There, you can see it. Alpha, alpha. Right, because this is the horizontal line, this is the horizontal line, this is a straight line that cuts both of them. Geometry. So, what is alpha? Well, you could use trigonometry to actually find a value for alpha in terms of s and h. And you know L in terms of those two already. But we can make our life a lot simpler because we don't want to know alpha. We don't care about alpha. We care about the cosine of alpha. And the cosine of alpha is adjacent over hypotenuse. S over L, or S over the square root of s squared, h squared plus s squared. Right? So I can just rewrite this as minus FA times S divided by h squared plus s squared, take the square root. Right? The cosine of this is the adjacent over the hypotenuse. Sure, you can work, if you've got actual values, you can find a value for alpha if you want to. But we don't care. We don't need it. And then we could just plug in what we've got for FA. So this is this stuff up here. So I can then write that the force in the x direction is going to be minus K Q times QA. Now, beforehand I just put the absolute value around the whole thing, but the only thing that could be negative in here is the Q or the QA. So I can just write it like this as well. Say I just care about the magnitudes. Divided by, put h squared plus s squared, but then the cosine is introducing another 1 over the square root of that, and an s on top. So I get s divided by h squared plus s squared to the 3/2, right? 1/2 power in here, and 1 power of h squared plus s squared from here. And that is it. If you have values, you can plug them in. That's the x component of the net force. Okay. Now let's do the y component. Well, the picture is the same. The picture is what we have up here. F net in the y direction is going to be, well, let's have a look. Let's start with FA first again. This is pointing down, right? I can see that. I'm not getting confused by signs. I know which way it points. It's downwards. My y direction is up. So this is in the negative y direction, right? A negative y component. So I'm going to put minus FA, minus because it's down, or, well, more strictly speaking, because it's down while positive y is up, right? It's the opposite direction. Times what? Well, in this case, it's the opposite of this angle. That's the sine of alpha. Now, don't go away from this video thinking that it's sine because it's y and it's cosine because it's x. I could have chosen to use this angle down here instead. Then it would be the other way around, right? Don't try to sort of learn by heart procedure, x cosine, y sine. No, look at the geometry. Which angle am I using? Is it the opposite? Is it the adjacent? That'll tell you whether to use sine or cosine, so you never have to ask. And now, what's the contribution from the other force? Well, the other force points straight up, so that's positive y direction, and there's no angle involved. So I'm just going to add plus FB, and I've got expressions for FA and FB they can plug in. So let's work this out, or just plug in what we got. What is the sine of alpha? Well, the sine of this angle is the same as the sine of this angle. Sine is the opposite over the hypotenuse. And again, just as before, I could work out the numerical value of alpha and then take the sine of it. But I don't even have to do that, because I don't care about alpha, I care about the sine of alpha. And the sine is h over L. So let me write this out. I get minus k QA Q, opposite order here, doesn't matter, divided by h squared plus s squared. That would be FA. Now the sine is h over L, while L is this. So I multiply this by h, and I get another power of a half down here. Oops, you can't see this. Here you go. I multiply this by h, and I multiply the denominator by the square root of what's already there. So that means that what I get is what's already there times 3/2. And then I add to it FB, which is K, QB, Q, divided by h squared. Right? This is h squared plus s squared. This is h squared. Why? Well, as we found up here. Well, because the green force, the distance between the charges, is this. For the red force, the distance between the charges is this. Don't mix them up. You've got the two expressions. And just as we predicted, there's no term anywhere that multiplies QA and QB, because forces add. I'm adding the force due to A to the force due to B, in both cases on the charge Q, which is why Q appears in both of them. In this case, there was only one force in the x direction, because the interaction between B and the charge Q was straight vertical. And now I've got my final answers, right? This is my the x component of my force. This is the y component of my force. The sum of those two. Now, if you have values, you can plug them in and get a numerical answer. If you want to convert this to a magnitude and an angle, well, let's do it. I'm not going to write it all out. I'm just going to assume now that we now have F net the x direction, and we have F net in the y direction, right? We do. Have them right here. There might be a complicated expression. If I try to write it all out in terms of those, it would be very complicated. It would be long. It wouldn't be conceptually difficult. It would just be long expressions likely to make a mistake. So I'm not going to do this. I'm just going to use these symbols here. I know what they are. I have numerical values for those, or I would have numerical values for those if values were given for all the Q's and S's and H and so on. Well, the magnitude of the net force is going to be F net in the x direction squared plus F net in the y direction squared. Take the square root. Right, it's going to be something like, this is a little bit to the left, this is up or down. To get the net force, I again use Pythagoras. Right, so if it looks something like this, and this is F net x, and this is F net y. What's for the angle? Well, if you look back at the original one, I don't strictly speaking know whether the downwards part of the red force is bigger or smaller than the upwards part of the green force. Right? If this one were a lot stronger than this, then the net force would be sort of down and left. Let me assume though that that in this case here, the green one, the upwards part is bigger than this one. I don't know, but I have to draw it one way or another. Well, then I can find perhaps this angle here. What is this angle? Let's call it theta. Well, in geometry, I have all sides of the triangle. So, I mean, I could use cosine or sine or tan. It's entirely up to me. I'm going to use tan because those two were kind of the original values I found. Right? So the tan of theta is F net y opposite over adjacent. F net x. And then theta itself, well, you just work this out and take the inverse tan, the arctan of the whole thing. And if it be in the other situation where, if you look up here, if this thing had been bigger than this one, so that overall the y force had been negative, then it would be pointing downwards, well then you could find that the downwards angle the same way. I'm not waiting for theta to be positive or negative or somehow to magically tell me, which way it is just from the sign. I mean, you can do it consistently like that, but you're going to get confused. You know which way it points. You can see it. So let me find the simple angle here, 20 degrees, 5 degrees, whatever it is. So now I've got a net force as a magnitude and an angle. I work the net force out as a magnitude and angle from the components, right? You can't add vectors without going to components. You can't add magnitudes, you can't add angles. You have to split your forces into components, add the components, and then you can convert back to magnitude and angle. And remember, don't get confused about what, say, to plug into Coulombs law over here. Which interactions are you looking at? You're looking at the interaction between those two? Okay, you're going to plug in Q and QB. Look at the interaction between those two. Plug in Q and QA. The interaction between those two, yes, it's physically there, but we don't care if we're asked to find the force on this one. So each single step, it's clear. Just don't get yourself confused. Don't try to guess what you have to plug in. Draw it. Ask yourself, what forces is this one experiencing? Okay, there are two other charges here. It's getting repelled by this one, getting attracted to this one. I draw them. I work them out individually. I add them because I understand vectors. You get yourself confused if you try to learn procedure. If you're trying to learn it saying, okay, so I first, just plug in those two charges and those two charges, and then I just, put, okay, h squared plus s squared on one, h squared on the other. Well, what if the problem looks different? You're going to get it wrong if you try to just replicate this sort of equation-wise. No, replicate the method of identifying the forces, identifying the interactions, asking which ones are relevant, analyzing them one by one, and then using the geometry and the vector addition and so on, the general math that you know. If I have 10 charges, it's going to be more work, but the procedure is the same. It's simple. It's long, but it's simple. If I have 100 charges, principle, it's the same. I probably don't want to do it. It would take me all day. Maybe I have a computer do it. But the method is exactly the same. If both arrows point in off at some angle, right? This one is not right above this one, but off to the side or something. Well, then I'll just do to the green one here what I did to the red one here, and I get a term here, and I get a term down here. But I'm never wondering, am I doing the right thing? Because I do it step by step. I know what's physically going on. I know what I'm physically caring about, right? The force on this one, the interactions between this one and each single other object that might be involved here. In this case, those two charges. I do not care about what the charges do between themselves. I hope that helps. You're not getting confused. You break it down into its individual bits. You make sure you understand what's going on first before you try to throw math at it. If you understand what's going on, you understand which way the forces point. Then it's just simple vector addition, and you know how to do that. Good luck.